Okay, I'm kind of having problems here because in this machine I don't have a PDF viewer. Finally. Okay, sorry about that. So, I'm gonna talk about graphics programming on EGA hardware, and I'll give you a glimpse of what's computer graphics back and now. So, this is the outline of the things we're gonna talk about. And let's start. About myself, I work as a research assistant for virtual reality and computer graphics. And let's start. So the term was coined back in 1960s by Hudson and Fetter. And basically what computer graphics did is a revolution in the way we interact with machines and how we today have a conception of graphics hardware. Most importantly, graphics hardware is not only used to draw on the screen nowadays, but also to run batch processes for visualization of data and simulation for physics and chemistry. So at the beginning, the modern interactive graphics are found in Sutherland's work, Sketchpad, where he introduced hierarchical data structures for basically representing computer graphics using recursive templates of data. And he also introduced new interaction techniques for making choices, pointing, and drawing. So basically the way we interact with the application. And then we had, in 1980s, we had raster graphics introduced by this built-in displays popularization. So we had basically bitmap to represent images on screen. So what is a bitmap? A bitmap is a binary representation of from a rectangular array of points called pixels on the screen. So each pixel has value and it's represented on the screen to form our final image. So the EGA adapter only allows 16 bits of color, and the memory addressing begins at A000, and it extends for as much as 64K. So a pixel is assigned. I mean, a pixel memory is represented as 4 planes in memory, and given a combination of those bits in memory, we represent a pixel value. The important thing is that all these 4 planes are considered as the same memory address. So the data in these 4 planes is then latched by a read memory, and
Should this be 16 colors or 16-bit color?
you're correct. Yeah. Yeah, totally correct. Yeah, because you only have these 4 planes, so you have only 2 to the power of 4 combinations. Yeah, 16 bits is kind of a lot. Yeah, another question was this. Right. Okay. Sorry. Okay, then we can modify and rewrite this memory. So this is I'm sorry for the bad photograph. I don't have a scanner. So this is the schematics for the EGA adapter, and here are the 4 planes of memory, and we have this the cathode ray tube to sync the video, and then you go to the output and you see things on the screen. Briefly about the VGA, as a bigger resolution and still uses the 4 planes of memory, but there is a selector of palettes, so you can with 6 bits addresses you can choose between different palettes. Okay, then we have APIs for graphics programming. introduced in the 90s with OpenGL and DirectX. Basically are an interface for programming this hardware, so you don't have to actually use the hardware directly, but you can interface with a library that does all the low-level resolution for you. Everything started with a fixed function pipeline. So basically, the programmer didn't have any choice on how to process its data into the GPU, but it could only input data and get the output. Everything was hard-coded into the logic. Then we have a programmable pipeline. Modern GPUs have a built-in programmable pipeline, meaning that a programmer can write his own shader programs to modify and work on his own data that he inputs in the pipeline. For example, we have different stages in this programmable pipeline. We have an input assembler where we actually feed data, a vertex shader where we modify this vertex data. Then we have optional steps. The other not optional step is the pixel shader, where you can code and modify the color of each fragment of your image. And then the rasterizer is basically what we saw before, that thing that converts your data layout into a raster on your screen. And this step is still not programmable. So this is just an example code of what you can do with your GPU. And well, nowadays we use GPU for computation. As I said, we have really higher level structures where you can just hardcode into memory, basically a bunch of render commands, and you just launch it for every frame. This is an example of a modern pipeline. Okay, but back on what we were talking about. So we have different ways to access the video memory. So we could code using registries directly on the adapter, or what I'm gonna show because of time constraints and simplicity is system calls. So using DOS, you can actually use system calls to tell the system to use the video memory as an array of characters, of bytes, where you can actually write your value and then blit it to the screen. So I'm going to use the mode 13H, and basically what we do is in this initialization is basically writing our mode and do the system call to actually change the value on the low level layer of the system to instruct the operating system to do what we asked. So using the video memory as a 2D matrix. Okay, for a real use of this code is actually this for malloc is just a memory allocation on the heap of the system. So this will basically represent our frame buffer when we actually write our image, our raster image that we have then to show on the screen. So basically this is some kind of double buffering that we're using. Well, this is just variables that we use for screen width, screen height, the size of the entire video memory we want to use, and then we see how we can actually draw a pixel on the screen. Basically, we have to calculate the offset into the offset into the screen matrix, and this is basically the pointer, the value of the address where we start actually drawing our pixels. So this is basically a write, and this is a read, where we can get the pixel value basically in the same way. Well, here's an example on how to draw an horizontal line. We basically, what to do is we calculate the address of the beginning of the line where we want to start drawing, and then basically we memset our color value of a certain length of the line starting from the address we just calculated. For a vertical line, we have the problem that we have to we cannot just mem copy into the array, because we have to skip lines into the 2D matrix. So we will loop through the rows of our matrix and just write the single pixel for each row of the matrix. I wanted to show also arbitrary lines, but the code would be really too long and doesn't really make sense on this slide. So I'm going to talk about this Bresenum algorithm. We basically want to know where we start and where we end, and given an approximation error for the horizontal component and the vertical components, we will draw our line. So this is the pseudocode to draw basically the line, and here is the check for the tolerance, and yeah, and then we loop until we reach our final point. So I also wanted to show an example on how to draw basically bitmaps. So instead of using mathematics to calculate the layout of our shape, we can actually write our shape into a file, into a binary file or whatever we prefer, and then read it into memory and directly write it to the video memory instead of calculating each pixel, each step. So here's an example of what you can do. So you can compose actually an atlas of sprites, and then read each frame into the memory. And with this method, you can also realize animations. So you can have animated characters. And there's another example of texture. So the only problem here that we have to solve is the synchronization of how many times we have to draw our screen. So the refresh of our render. Well, in the early days, I guess that really crappy games were using just while loop, so they were synchronized with the processor. A better technique could be just to calculating a frame time and then just drawing if needed, so we can have a controlled render loop. Well, I said it was really short, so questions? Probably.
You've actually made an array off screen and worked in that instead of
Yeah,
working in the
yeah.
screen.
So one is actually read into the screen, so you basically display that part of memory. You basically render into an off target, so when it's time to switch the screens, you always have a buffer where you can draw. This is used as a technique used to avoid screen tearing, so you don't see some dirty memory on the screen, basically. Well, if there's no other question, I guess thank you for the attention, and sorry for the beginning. No. Actually, there are a couple of good references for C programming. There is well, if you Google it, there are a lot of material. There's a lot of material on the internet. Plus, there is a really good book that's called graphics programming in C, and there you can find basically the code that I put on the slides was taken from there.